astronomers spotted a new visitor from deep space, 3I Atlas, but it was far brighter than expected and showed no gas. What could explain this strange light? Is it a giant 20-kilometer nucleus, or just a massive cloud of dust? There's even a third, more speculative idea, that it's a compact source of light shining on its own. This is an open case. Every new clue moves us closer to an answer. What is this mysterious object, and what will it reveal? If you enjoy following real-time astronomy mysteries, like watching JWST data reshape how we see distant galaxies, this is one of those cases. It is a careful investigation, clues, competing hypotheses, and the tools astronomers use to filter evidence. You'll see why 3I Atlas appeared unusually bright, how its light faded in a steep profile, why no gas showed up in spectra, and the three hypotheses put forward in response. The consensus view is that ordinary comet physics should explain it. A working hypothesis is that dust or nucleus size accounts for the glow, though alternatives remain under study. And it all begins with the first clues in the case. The first clues in the case. Why would an object passing quietly through interstellar space shine hundreds of times brighter than expected for its type? This was the first question raised once astronomers began following 3I Atlas. To see why it was striking, it helps to recall the two earlier visitors. The first, 1I ʻOumuamua in 2017, was faint and unusual in shape, seen only as a speck that large telescopes could just track. It gave off no gas and no dust, behaving more like bare rock than a comet. The second, 2I/Borisov in 2019, looked very different, releasing gas and dust in a way familiar from ordinary comets of our solar system. Together, these formed a kind of baseline, either an inert, rocky shard with little reflection, or a comet showing strong outgassing. 3I Atlas did not line up with either case. At discovery, it was still around 400 million kilometers away, beyond the orbit of Mars. Even at that distance, it appeared much brighter than astronomers thought possible. Brightness is measured using magnitudes, a system where smaller numbers mean brighter light, and a difference of a few magnitudes corresponds to a large change in brightness. At roughly that distance, Borisov was faint and only beginning to outgas. Yet Atlas registered about magnitude 16.4, already brighter than both Borisov and ʻOumuamua under similar conditions. For astronomers, that single number immediately stood out. For most comets, light is explained by dust scattering sunlight and gas releasing faint glows at specific wavelengths. As comets warm, they throw off material, and telescopes can easily detect spectral signs of molecules like carbon or oxygen. But Atlas did not follow this script. Early spectrographic measurements showed no gas features at all, only a smooth spectrum consistent with sunlight bouncing off dust or solid matter. That left no obvious process to explain its brightness. A luminous coma without gas emission is not what comet models predict. That mismatch led scientists to weigh early hypotheses. One idea was that ATLAS had shed a large cloud of dust in a single event, producing the strong reflection. Another possibility was that the central nucleus was unusually large. A body on the order of 20 kilometers across might reflect enough sunlight to explain the observed glow without releasing gas. But this too raised problems. Interstellar fragments that survive long journeys are expected to be smaller or eroded, not massive intact blocks. A nucleus that large would be surprising in itself. None of these ideas fit smoothly. Without gas, a sudden outburst of dust is difficult to explain. Yet, a 20-kilometer nucleus would push the limits of what models predict for bodies traveling across interstellar space. That tension sharpened the mystery. The data at the time showed a bright magnitude, a distance much too large to expect visible activity, and spectra without gas lines. Each piece served as a clue, but none alone provided a clear answer. The question became, if not gas-driven activity, then what accounted for the intensity of that glow? Observers knew they would need more than just a brightness measurement. They had to study how the light itself spread outward, looking for patterns only visible in the distribution of the glow. Following the light trail next clue, the way the light fades outward, the brightness profile. Instead of asking only how luminous 3I Atlas appeared, astronomers now measured how that brightness declined with distance from its center. This approach creates what is called a radial brightness profile, a record of how quickly the glow diminishes as you move outward from the blurred image of the object. In plain terms, the brightness profile is simply a graph showing how fast the light weakens away from the middle. For comets, the expectation is well known. Dust and gas scatter sunlight, producing a halo of reflected light that thins gradually rather than suddenly. The slope of the curve, how sharp the decline is, serves as the diagnostic. A shallow slope points to scattering across a wide cloud, while a steep slope hints at light concentrated near the center. To picture this, consider one analogy. Hold a flashlight in the dark. Most of the brightness hugs the beam, and just off-center the light drops off abruptly. Now, think of a lantern in fog. The haze diffuses the light broadly, spreading it out more evenly into your surroundings. Comets almost always resemble the lantern case. Their light profile spreads in a steady, predictable decline. Astronomers use that well-tested baseline to compare with unusual cases. To measure the profile of 3I Atlas, astronomers turn to the Hubble Space Telescope and large ground-based observatories. Neither can resolve the core directly at distances of hundreds of millions of kilometers, but both can record how the blurred glow behaves outward from the center. Hubble's advantage is its freedom from atmospheric distortion, providing stable images that allow careful measurement of faint halos. Ground-based telescopes contribute by observing repeatedly over weeks, which helps confirm whether the slope remains steady or shifts. Together, these observations can be compared against comet models. The profile that came back was striking. One published analysis reported a projected slope near -3, which corresponds in three-dimensional terms to an emissivity profile around -4. That is much steeper than the typical values produced by sunlight scattering from dust. In fact, such a slope is closer to what might be expected if a concentrated light source sat close to the center, illuminating nearby material. Yet, astronomers emphasized caution. Brightness profiles are among the most difficult measurements at these scales. The images of ATLAS were low in resolution, and the glow itself faint. Blur from both instruments and distance can exaggerate or distort slopes, making exact numbers hard to interpret. As one researcher described, the result is a bit difficult to interpret, with uncertainties about whether the slope is truly so steep or partly an artifact of limited imaging. Even with this caveat, the possibility raised important implications. If the sharp decline is real, then the object may not need to be massive to explain its brightness. A small body, strongly illuminating dust close by, could mimic the glow of a much larger cometary nucleus. This contrasts sharply with the standard reflection model, which requires a nucleus perhaps up to 20 kilometers across to scatter enough sunlight. In hypothesis form, the steep profile suggests two possibilities: either an unusually compact bright center, radiating out through nearby dust, or a transient cloud of fine particles dispersing more rapidly than seen in ordinary comets. Both require conditions not typical of standard comet activity, and both need further observations to test. The main point is that, at this stage, astronomers could not rely on brightness alone to settle the case. Instead, the profile data introduced new uncertainty, whether scattering from dust truly explained the observations, or whether a central emitter might be involved. In the logic of an investigation, this was the point where clues began pointing to more than one path. The measurements did not settle the mystery, but they narrowed the options and raised sharper questions. That laid the groundwork for a next step that resembles a panel of detectives, each presenting a different theory about what the evidence could mean. The hypotheses and the tools. The consensus among many astronomers, based on the available images and spectra, favors a dust-dominated coma, sunlight scattered by fine particles surrounding the object. Yet that explanation does not fully match the data, leaving space for competing ideas. Three main hypotheses remain under consideration: that the brightness comes from a dust coma, from a very large reflective nucleus, or from a compact source of light near the center, acting as a direct emitter. The dust coma hypothesis is the most familiar. In this idea, grains lifted from the surface form a surrounding cloud, and sunlight scatters off those grains to produce the halo we see. What weakens this scenario is the lack of gas detection. Gas is usually the driver that carries dust away from a body. Without it, dust tends not to escape in large amounts. Diagnostics that could favor or rule out this hypothesis include spectroscopy, sensitive to emission lines of water vapor or carbon monoxide, which so far have not appeared, and phase angle studies, since dust halos scatter in predictable ways depending on viewing angle. The large nucleus hypothesis proposes that the main body of 3I Atlas is simply far bigger than expected. For reflections to match the observed brightness, the nucleus would need to measure on the order of 20 kilometers across. That size is large enough that thermal emission should be measurable in the mid-infrared, radiated heat proportional to such a wide surface area. Yet no clear infrared detection has confirmed that signal, and interstellar travel is thought to grind objects down rather than preserve such giants. This mismatch makes the large nucleus idea difficult to sustain, though not fully excluded. The most speculative idea is the central emitter hypothesis, that the object produced light itself. Model estimates suggest that if this were the case, a compact luminous source, smaller than about 100 meters, could generate the observed output, comparable to a luminosity on the order of 10 gigawatts. That is far smaller than the reflective model's requirement of tens of kilometers. But there are challenges here as well. For instance, a thermal source cooler than about 1000 Kelvin would radiate most strongly beyond 3 microns, in the infrared, which does not match the observed optical glow. And unlike with dust coma or reflected sunlight, astronomers have no known category of small icy bodies shining on their own. This idea therefore remains outside the mainstream and depends heavily on how one interprets the steep brightness profile. The contrast in potential sizes brings the stakes into focus. The reflective nucleus hypothesis makes 3I Atlas a giant, larger than most comets seen in our solar system. The central emitter idea would reduce it to a very small, luminous source, much closer to the scales of ʻOumuamua or Borisov. Dust coma models sit in the middle, invoking familiar processes but pushing them into unusual conditions. Each hypothesis explains part of the evidence while straining under other parts. Astronomers test these ideas with several tools. Multi-wavelength observations let them check behavior across ultraviolet, optical, and infrared light. Ultraviolet can reveal gas, optical tracks, dust reflection, and infrared constrains nucleus size or thermal processes. Spectroscopy hunts for emission lines of key molecules. Detection would strongly favor the dust coma model. Phase angle monitoring, measuring how brightness changes as the angle between sun, object, and Earth shifts, helps separate scattering in dust from reflection off a solid surface. And of course, sharper resolution, from Hubble, future telescopes, or ideally a spacecraft flyby, would give the clearest test by resolving whether a coma is real or just blurred light around a compact source. Each method pushes the balance for or against one of the 3 hypotheses, but none so far has delivered a decisive answer. Taken together, these approaches show the limits of current data. Spectra detect dust but no gas, undercutting the classic coma case. Infrared signatures that should appear from a 20-kilometer nucleus have not been seen, arguing against the giant nucleus model. The steep brightness profile fits a compact source but may reflect low resolution, imaging artifacts instead. The central emitter remains possible in principle but speculative in practice. In short, all 3 remain on the table, with none fully supported and none completely excluded. This scientific uncertainty carries its own lesson. Each hypothesis fits one clue set, but struggles with others. The data force astronomers to hold competing ideas in balance rather than close the case too quickly. It shows how astronomy advances, by careful steps, weighing probabilities and waiting for better evidence. And it leaves us in the position to ask how such restraint matters when an unusual interstellar visitor may never grant definitive answers. Conclusion. 3. Atlas highlights how astronomy advances by testing each clue against structured possibilities. Certain observations would help weigh the main hypotheses more sharply. A sensitive mid-infrared detection of a large, cold nucleus would favor the reflective model. Repeated spectroscopy finding gas lines would revive the classical comet hypothesis. And, if future data confirm a steep brightness profile while showing no thermal signature, that would strengthen the compact emitter alternative. Each path remains open until measurements close it. This is an open case. Each new observation is another piece of evidence that moves us closer to a conclusion. Improved telescopes and rapid response probes may one day offer the definitive view. In the meantime, let us know in the comments which type of evidence you think would be most decisive. And if you value calm, evidence-first explainers, consider subscribing for more investigations like this.